Yep. Okay. Well, everybody, we're getting towards the end of the course. Today is week 10 out of I want to say 14 or 13, maybe even 12. I honestly forget. I don't know. You're getting there, you know? And honestly, I think this is the hardest unit, so don't feel too bad if you're still a bit shaky on some of this stuff, but let's do some practice and try to become a bit more confident. Today is 11/14, and yeah. So to start off, I think today, just because there's like kind of a lot of stuff in this unit, I'll give a kind of I'll give a sort of in-depth, but not as in-depth as I probably should, overview of just like the equations and stuff you've learned. And I think it'll just be more useful to do practice problems. I think that's always just more useful. So, yeah, without further ado, this week you learned about complex power. The idea here being that if I have some circuit, right, and it has some voltage, but we're in the frequency domain, and we got some current and we got, I don't know, some things, right? We can express the power of each of these quantities as some kind of complex power that we call S. And S is equal to 1/2 of V times I conjugate. And if you don't remember, the conjugate of some complex number. So if this equals a plus JB, then Z star would equal a minus JB. And likewise, if Z equals a to the e to the j theta, then Z conjugate would be a e to the negative j theta. So don't get that wrong. That should be the easiest part. So this is our basic equation for complex power. You can put a bar on top of the S as well if you want. And the complex power, we have to use complex power because in circuits, when you have a sinusoidal input, there's kind of two things going on when you're looking at how things like resistors are uh, interacting with that power versus how things like capacitors and inductors are interacting with that power. What you find is that resistors, all they can do is resist. So they always dissipate power as real energy. So they turn it from the electrons moving into heat, right? But the capacitors and inductors do something different. They store the energy in some kind of form. The capacitors store it in the electric field, the inductors store it in the magnetic field. And while that isn't dissipating the power, it is storing it. So it is removing it from the circuit. And we model that as complex power. We model the combination of those two as complex power. So as a reminder, so I'll go through some more equations here. So just as a reminder, V bar, that's going to be some V naught values. That'd be the amplitude times e to the j, and we're going to call it phi V. I bar equals I naught e to the j phi I. And then if this is our S, then we can also write S as 1/2 V naught I naught e to the j phi V minus phi I. Because if we have I conjugate, then it'll be this, right? This is I, but I conjugate would then be negative that. And this is what would happen if you multiplied those two by exponent rules. Um, so moving on. How you are probably used to seeing this by now is that we can also write this as P average plus JQ, where P average is the average power and Q is called the reactance. So this P average is like your real power, what's actually being turned into heat in your circuit, and your Q is kind of representing the energy that's being stored. And some more equations for this. We got that. So simply you can write that P average equals the real part of S, which is equivalently, uh, you can write it as S times. So if we moving back a bit, I'll give one more way to write S. We can write this as like S equals S naught e to the j phi. I think they called it phi z. I'll call it phi s because that makes more sense. Um, so this is equivalently like S naught cosine phi s, whereas Q would be the imaginary part of S, which is S naught sine phi s. That's just like if you have a complex number and you have your real part and your imaginary part, that's just how it works out. Um, so then there's a lot of stuff since we know that V equals IZ, right? There's a lot of rearranging we can do with this power equation. So one of the most useful ones is you can say power equals, oh wait, one other thing, I'll talk about RMS, so root mean squared. That's basically like if you have your sine wave and then you were to flip it all over and then find the average of this. That's what root mean squared means. But it's basically just VRMS equals 1 over root 2. That's what you end up getting, V. So likewise, IRMS equals 1 over root 2I. So we can also say that, move this down even a tiny bit more. We can say that S equals VRMS times IRMS conjugate. And that's nice because it just gets rid of the 1/2. It makes it look a bit nicer. Yeah. So going back to more useful ways to write S that might make it more useful when solving circuits. We can write it as 1/2 uh, V squared. So this will be basically this is just going to be a V naught squared. The way you get the magnitude of a complex number, if you remember, is V times V conjugate, and that would have the imaginary components cancel, and you would just be left with V naught squared. So V naught squared, or the magnitude of V squared over Z conjugate. So that's one way to find the power. So if you have, like, if we were in this circuit and we knew the voltage from here to here, and we know this, then we can use that equation to find our complex power. Other things you can say S also equals what is this? 1/2 Z times the actual current squared. And then there's like more ways you can write the equations, but you can like kind of if you know this and you know the two most important ones I'll like box in red, I guess. If you know this and you know this, you can plug things in and rederive every other equation. So just remember these two if you're going to remember any of them. It's kind of unrealistic to expect you to remember all of these. These are just like different ways you can rewrite it. Okay, then moving on. Oftentimes in circuits, we care purely about P average because that's like the actual power that's getting used. And one way they sometimes write the complex power is they'll give you the P average along with a power factor. And this power factor is simply the ratio of P average to S. And after doing some simplification, actually I can just write it out. So this is like P average is going to be I could write it. It's not worth writing it out. Anyway, it ends up being just the phase of the complex number. So this equals cosine of phi s, which is the same as cosine. The more useful form is the cosine of the voltage, the cosine of the angle of the voltage minus the angle of the current. So that's your power factor. Basically, if you look here, right, that's a measure of how much of this, it's like the ratio of here to here. And that ratio is like if we normalize it so that this has a length of 1, then this is just the cosine of this angle, and this angle equals 5v minus phi I. So the power factor, right? Then the power factor would be a number between 0 and 1, where 0 is it has, or I guess it could also be, yeah, between -1 to 1, where there's a table he has somewhere, like a pretty in-depth table. Oh wait, no, it can actually only be between 0 and 1 because reasons. 0 and 1. Where 1 is for purely resistive loads. So that means your Z or your impedance has no imaginary value, and 0 would be purely complex loads, so you have an inductor or a capacitor. Um, yeah. And then last but not least of things I'll just mention at the beginning here is maximum power transfer. If I have some circuit and then I convert that to a Thevenin equivalent, let's call this Z, I'll just call it Z circuit, ZC. Okay. And then we have, we know what this is. This is our V. And then we want to find, okay, what's the maximum power that this circuit can transfer to some load ZL? What we find is that the maximum power is found when ZL equals ZC star. So when it's the conjugate of that internal load to the system. And the power average that you find, because the power average is what we care about here, is the 1/8 times that Thevenin equivalent voltage squared over our load resistor, or over our ZL, I guess. Okay, so there's like a lot on this page. Really, if you need three things to remember that first equation. Remember this, and this. And if you remember those and actually understand what they're saying, then you should be able to kind of derive everything else on this page, or at least be like, if you don't really need to derive any of the other parts, but you should be able to like, you have all the variables there. You can connect them all in some way, hopefully. Um, yeah. Again, this unit is just like a lot of like the complex number math is hard. It's really easy to mess it up. So don't feel too bad, but do try your best. Yeah. So now, without further ado, I will just get into some practice questions. Oh, I accidentally just closed some. Did I? Wait, no. Okay, we're good. Yeah. Okay. So yeah, this is a let me pick one. That looks nice. Okay. Uh yeah, that's a pretty chill. Okay, so you might have a question like this, where we have some power source. Everything is in the frequency domain already. And this is 6 ohms. And it says find average and reactive power for the inductor. So right away, one thing you can actually, I should have mentioned this a bit more explicitly earlier, but if you're looking at components on their own, um, a resistor will only ever have real average power, and an inductor or capacitor will only ever have reactive power. Neither of them can do both. They can only do one at a time. So you should just be able to fill that out immediately if you have a question that's asking something like that. Um, but the sources can be providing any combination of them. So, okay, these two together, right? This is basically saying find S, right? Because S equals P average plus JQ, right? So we look at this and it says, okay, we want to find the power associated with this. So that inductor, that means we need to find the voltage across the inductor and the current across the and the current through the inductor. So to do that, you can do it in like any way you want. To me, the easiest way to do this is just some kind of node voltage. Here you have one node of importance. You say ground is down there, and then you write out your equation. So V1 minus 24 over J3 plus V1 over 2 plus V1 over minus J6 equals 0, right? Uh, and then you simplify and solve. It's not any really straightforward way of doing it. Or I mean, this is a straightforward way of doing it. It's just like the same as what you've done so far. So, we take out the V1. We got V1 times 1 over J3 plus 1 half plus 1 over minus J6 equals uh 24 over J3. You could put this directly into your calculator if you wanted to, but I think you're not supposed to do that anymore. So what we do here is multiply everything by J6, I think. So V1 times, if I multiply this by J6, I get -2. This by J6, I get negative, or no, it would be +2, sorry. So we get 2 plus, what is this? J6, yeah. Yeah, 2 plus, I'm overthinking myself. 2 plus 3 plus 3J real. 3J plus or minus 1 minus 1 equals, and then this would be times 2, so equals 48. So then we get that V1 equals 48 over 1 plus 3J. And if you evaluate this, you can either like put this into phasor form and then do the division, or you can multiply by the conjugate. I'll multiply by the conjugate here. Do it in any way you want. You're just looking for V1 in some kind of form you can use easily later. So this would be 48 minus 3 times 48 is 144J, and that would be over 1 squared plus 3 squared would be 10. So that would get us 4.8 minus 14.4J as our V1. So then if I want to find the current, or if I want to find the voltage across that inductor then, right? You just say, okay, the voltage across the inductor is the voltage on the right minus the voltage on the left. Just the voltage difference, right? So VL equals 24 minus 4.8 minus 14.4 J. So we have to do this because it's not 0 here, it's 24. So the difference between here and here is 24 minus that. Okay, so you do this, and you get 19.2 plus 14.4 J. And that's our voltage difference across the inductor. So then if we want to find the current through this inductor, well, first it would be better to have this in phasor form. So we can say, okay, VL, that's going to be equal to, and then, use your equations, the angle is going to be the tangent inverse of 14.4 over 19.2, which gets us, my calculator is in radian mode. Let me switch that over, which gets us e to the j 36.9 degrees. And then our magnitude is going to be that 19.2 divided by cosine of that number we just got, which is 24. So, second, yeah. So it's 24. Yeah, so it's theta equals tan inverse of 14.4 over 19.2. And then the V naught equals the 19.2 over cosine of theta. So then you get that. Okay, so then if we want, so remember, our goal is to find S, which is equal to 1/2 V bar times I bar conjugate. So we have V, now we need I. So if you have the voltage and you have the impedance, you can just find the current directly. So I bar L is going to be equal to VL or V bar L over that J3. So that's equal to 24 e to the 36.9 J over J3 can be written as 3 e to the J90. Um, you can either go through the whole tangent process or just like if this is your complex plane, if J3 is up here, just if this is your real and this is your imaginary, if this is 3J, like it's a 90-degree angle. So it's 3 e to the J30. Um, you do this out, you get 8 e to the negative J 53.13. That's just some subtraction. And then finally, at the end here, we're going to be doing, we have all the components. So S equals 1/2 V bar I bar star. So that's 1/2 24 e to the 36.9 J times 8 e to the, and now this is the important part, it's I star. If you forget this star, then you'll get a number that does not match what you should expect, which is, as I said at the beginning, we're looking at the complex power of this inductor. Inductors cannot dissipate real power, so we are looking for a number that has zero real part, right? If you do not take the conjugate of this, right? We have I, we want to find I star or I conjugate, then you'll get something wrong. So here, this is 53.13, not negative 53.13. And this works out nicely. I'll actually round this to just 53.1 because that will make it look a bit nicer here, right? So then if you multiply these two together, okay, you get 12 times 8, which is 96. And then 36.9 plus 53.1 is just 90. And so this is then equal to 0 plus J96. And that would be volts. Oh, this is a kind of important thing that I've missed at the beginning. The units for stuff in this is kind of weird because they don't use watts because it's like not watts. It's weird. So if we say that the complex power has units of volt amps, and then the average power has unit of watts, and this has volts amps reactive. So make sure you write those when you're, doing the question. So going back here, right? The question said find the average power and the reactive power. So that means our power average would be 0 watts and our reactive power Q would be equal to 96 volts amps reactive. And that would be your final answer here. So, it's like pretty straightforward. It's just a lot of complex math. Make sure you don't get bogged down in the math, and you should be okay. Okay, another thing you could have on your quiz tomorrow, more than likely, is going to be a Thevenin. I'm not sure you will. I'll do one. I think I think you've learned. Yeah, those were like covered on. I think those were covered on Monday, judging from his notes. So I'm gonna say you might have it. Yeah. So with that said, I'll do, yeah. So by Thevenin, I meant like maximum power transfer. So Here, we have kind of a funky looking circuit. If you notice here, the thing is upside down. So make sure you look at your circuits carefully. You don't want to let Zorman trick you. And yeah, someone saying something? No? Okay. If anyone has any questions as I'm going, just feel free to say something in the chat. I have it open. I will look. Yeah. So the question is find the the impedance ZL for maximum power transfer and find what the average power of ZL then is. So let's get started. So the first part is actually pretty straightforward, right? I can call this A and B. And as I said before, right, for the maximum power transfer, we want our ZL to be equal to the conjugate of that Thevenin equivalent resistance. So for that, that means we need to find the Thevenin equivalent between A and B. So we can redraw this circuit in the way that we do to find Thevenin equivalence. So that means that our voltage sources are eliminated and our terminals now become open, right? So I'll actually just erase these. And now we just want to find the equivalent impedance of this circuit. So to start, we have these two are in parallel. Or no, sorry, my bad. These two are in series and these two are in parallel with this. So this will end up being Z equivalent equals 2 minus J2 in parallel with J2. And that would be 2 minus J2 times J2 over 2 minus J2 plus J2, right? And if we do the math on this, this becomes all that's over 2, and then it's J2 and minus J2 times J2 would be 4, negative 4J, but it's squared, so it would be plus 4, I believe. Oh, silly mistake. This is a 2 times J2, so this would be J4. And then divided by 2, you get 2 plus J2. So that would be our Z TH. And then our ZL, as we said earlier, the maximum power will be transferred when ZL equals the Thevenin or the conjugate of ZTH. So that means our ZL would be 2 minus J2. So that would be the first part of our answer. Pretty straightforward. It's just a Thevenin equivalent resistance. Don't overthink it. And then after that, we want to find, okay, now what is the power that is being transferred? What is the actual power that's transferred here, right? And so what we do then, right, is we want to find, well, there's a couple ways. I will see what this answer I have here does, but I might disagree with it. Oh, actually, okay, this works well. Yeah. Okay. So if you recall, the equation we had from before is that the power average that you get out of it is in terms of VTH. So that's the Thevenin equivalent voltage, not like the actual voltage. So we actually don't have to care about what this voltage would be in the actual circuit. We only have to care about what the Thevenin equivalent voltage would be. So that means if we take this circuit again, And now we're looking at the Thevenin equivalent voltage. So I'll write the equation that we're shooting for, that power average equals 1/8 VTH squared over RL or ZL. Let me make sure I wrote that right. Yeah. And this equation can be derived from like first principles, but it's like not really necessary. So now we just want to find our VTH, and that would be the voltage between A and B. And to do that, like you can do it any way you want. Um, could do it with just a voltage divider, and that seems to be the easiest way to do it. So if we say, you know, we're calling that 0 volts. I mean, it already basically is. Keep in mind this is upside down, so don't forget that. But what we have here then is that the voltage from, I guess, B to A here would make a bit more sense to do. And it's going to be VTH equals, so we have our voltage divider, so J2 over 2 plus J2 minus J2. That's so this one, the math is actually pretty easy and nice for you, times 24 volts. So that's going to be J2 over 2 times 24, which pretty simply is just 24J, right? And then, so it's 24J there, and yeah, so we have that Thevenin equivalent voltage. And then even though, wait, okay, yeah. So that's the voltage difference between this point and this point. So then the difference between this point and A, so between B and A would be actually this and then plus 12 volts. So sorry, this would be a bit of a notation error here. The nice thing about power is that the sign of your voltage doesn't matter when you're dealing with power because it's all just like you're just going to get a number, and power can never be negative for like a load. So here you should end up getting like it I'm honestly not sure since this is upside down, like it would probably be better to like flip the whole circuit over to make a bit more sense in your head. But here, like you could, I guess it would be a bit more consistent to just with what we've done in the class so far to say that this is positive and this is negative. So then this would actually be a negative 24. I'll do it like this to make sure it's actually doing it properly. So if that's negative 24 between, yeah, so like I said, if it's negative 24 between here and here, then between here and here, it would be negative 24 plus 12. So then this is our VJ negative, or yeah, VJ2. So then our VTH would be VJ2 plus 12, which would then be 12 minus 24J. So then, last but not least, we want to use that equation we said earlier. And for that, we have to find VTH squared, or the magnitude of VTH squared. So that, just by the definition, is going to be VTH times VTH conjugate, which is going to be 12 minus 24J times 12 plus 24J. And that's going to end up being equal to 12 squared plus 24 squared, which I honestly don't know off the top of my head. It's going to be like 144 plus some other number, 720. So we get 720 as our VTH squared. And then if we plug this into our final equation, that power average equals 1/8 of that VTH squared over, and then, oh, actually, so since it's power average, I actually had this equation wrong. Yeah. So this here is actually just caring about the resistive component. And I'll change that here as well. So if we write our impedance as like ZL equals R plus RL plus J pi L is the convention, then this is just the resistive component for the power average here. So if we have this, then this turns into 1/8 times 720 over 2, which is 1/8. So 720 divided by 2 divided by 8 gets us 45 watts. And that would be your final answer here. Okay, and I still have more time, so I'm just going to do like one or two more questions.
Could you find the complex power using that formula with the ZL instead of RL?
So I don't think so. I'd honestly have to like go through and check if that actually I don't think it works. The reason it wouldn't work is because since this formula is using VTH here, I think it's kind of like it's already been solved. So if you really wanted to find it properly, what I would do is you'd have to go back to this initial circuit because the VTH here is not going to be the same as what you have here, I think, because the current will be split here and that'll end up messing with it. So if you want to properly find the VS, or if you properly want to find the complex power, I think you'd have to like do an actual node voltage equation about this point, and then you find this voltage, you add 12 to it to get this point, and then you also find what this is, or you'd say this is 0 at the beginning probably. And then once you have the voltage at A, the complex power, you would use like this equation. And this one would be the best one there because you have the voltage across it and then you divide that by that. Can I explain the voltage division part again? Oh yeah. So hopefully that answers your question. So if they're asking about a maximum power transfer question though, they're like this is the equation that he taught in class. They're definitely only going to be asking about the average power. So you shouldn't have to worry about that too much. But yeah, can I go over the voltage division part again? Yeah. So if we want to find the voltage between A and B here, right? So we want to find the voltage between these two. Then what's going to be very similar to that, because this is just a constant voltage difference. So that all this is telling us is that this point is 12 volts lower than this point. So if we find the voltage between these two and then add 12 to it, then we get the voltage between here and here, which is the same as between here and here. So what we do then is this is the same as if you had like some voltage and then a resistor and then a resistor and then a resistor, right? This is R1, R2, R3, and this is V. Then the voltage across VR2 is just the proportion of the resistance basically. So R2 over the total resistance, which is R1 plus R2 plus R3, and then times that total input voltage. So here, I'm basically doing the exact same thing, just with imaginary numbers, right? You got J2 is the target one, and then on the bottom, we have 2 plus J2 plus negative J2. And then multiply it by the input voltage, which here, since this thing is upside down, is negative 24 volts. And then this is just simplification to there. Yeah. Okay. Moving on. Okay, here's a power factor question covering all the bases. So we got 2A, we got 20, negative J10, J5. Okay, so it says calculate the power factor associated with the current source. So first off, what is this question actually asking? So it's asking you basically to find S and then find the like angle of S and then take the cosine of that. Because if we remember, the power factor, or alternatively, actually, you find the voltage and the current and then take the cosine of the angle of the voltage minus the angle of the current. This is definitely the better way to do it. Yeah, you can do it in either way. There's two ways to do it. Both of them will get you the same answer. Um, and if we, yeah, this is just the power factor by definition. If we look back here, right? That's what it is. I'm gonna take a sip of water and then I will go. So, how do we get started here? So, what you'd want to do is very nicely, as you can see, these are all the same node. So, this lends itself very well to node voltage. So, if I just call this V1, then I can say, and we call this like ground, you can say V1 over J5. Let's start with minus 2 amps because they got minus 2 going in. And then we can say all three of these are going out. So minus 2 plus V1 over J5 plus V1 over minus J10 plus V1 over 20 equals 0. Multiply everything by minus J10, we'd get, or by just J10, you would get J20 plus, let's see, this would be 10 over 5. That's just 2V1 minus V1 plus, oh, I should multiply by J20, whatever. 1 half J V1 equals 0. Realistically, I should multiply by 2 again to make this look a bit nicer. So we got J40 plus 4V1 minus 2V1 plus JV1 equals 0. Move things around a little bit. We get, let me make sure I'm doing this right. Uh, yeah. Yeah, this is fine. Okay. So, yeah, we put minus J40, and then this would become V1 times 2 plus J. And then if we divide this to the other side, we get minus J40 over 2 plus J. And yeah, I think that's right. Um,
Where did the 2 amps go?
the 2 amps, so this was the 2 amps, right? And then multiplied by J10. I should have multiplied by like J20 to make it all go away, but I multiplied by J10 and then minus 2 times J10 equals J20. And
Gosh,
that was carried through to there. Okay. So moving on. And then if we want to simplify this a bit, right, we got this can be written as, yeah, there's probably like a better way to do this, but this way like works fine. So this is e to the negative j90 over and then 2 plus j. That's going to be tangent inverse of 1 over 2, which I should be able, I think that's just like, I don't know. Tangent inverse of 0.5 is, oh no, that's not a nice number. Okay. It's just a 26.57-ish. And then if we take what is it? 2 over cosine of that, we get 2.236. So then we got 2.236 e to the j 26.56. And then if we do this nice subtraction, let me make sure we actually get the right number. Oh, and this is that right? I think I'm missing something somewhere. Um, because I'm supposed to get a different phase. 0.24 e to the Where did I miss it? Um, oh, okay, I see. This should have been negative, this should have been negative, this should have been positive, this should have been positive, and then this is a positive. Okay, there we go. So, and then this gets you 17.86 e to the j 63.43 degrees. Okay, there we go. So then moving on from there, we have our V1, and then if we want to find, oh, this is actually like a really short problem then. Okay. Yeah, because as I said before, right, the power factor is equal to the cosine of phi v minus phi I. So here we found that is phi v, and the current. So again, we're looking at from the perspective of the source, right? So for the source, the voltage at V1 is going to be the voltage of the source, right? So if we have the voltage here, then it's like very straightforward, right? Because since we know the current, it's given, the current is 2 e to the j 0. So phi I equals 0 degrees. So then we can just say the power factor is cosine of that 63.43 minus 0, which will get us cosine of that equals 0.447. And that would be the your answer for this question. You can also do it in like a yeah, just do it that way. That's the best way to do it. Like make it as simple as you can, especially when it's just asking about one component. So yeah. Okay. I can do still one more question. How do I know the current angle is 0? We know the current angle is 0 because it's given. So again, since we're looking at it from the perspective of the power source, it says calculate the power factor associated with the current source. So we only care about the current and power, we only care about the current and voltage on the current source. So the current through the current source by definition is 2 amps. And 2 amps in like the frequency domain is 2 amps with an angle of 0. So it's just kind of given to us. So this question is pretty straightforward. If you wanted to find like the power of this inductor, then you would have to do, okay, I take my 2 and then I do like some current division or something like that. And it would be more annoying, but or you just like do V1 over J5 and then you could get a current there and then you could find a power there if you wanted to. Yeah. Okay. Surely I can find one more question that doesn't look too. Actually, I should do the bad questions. But okay, I could do that. Sounds like interesting. Yes. Did I do this one yet? Yeah, I did that one. Okay, and then I'll do like a funky op amp question here. Actually, this is not relevant. Hold up. Uh, yeah, this one, I'll do this one. I don't really think you'll have a question like this on the exam, but this is just like kind of good to show that again, everything is pretty similar to what you've done before, just the equations are slightly different and everything is complex numbers. Okay, so this question is find the complex power of ZL. So what this means is that at the very simplest level, right, S equals 1/2 times V bar times I star. So here, since the bottom of this is grounded, V naught will be our V. And then once we have V naught, we can just divide V naught by this number to get the current. So basically, we just have to find that V naught. And you guys already pretty much know how to do that. This is nothing particularly new here. So if I call this Vn, this is Vp, Vn equals Vp equals 0 because it's an op amp and this one is grounded. Um, so then we can say that at Vn, right, we got Vn minus, and then this was 2 volts. So Vn minus 2 over 200 minus J500. That's just the sum of these two. And then plus Vn minus V out over 2400. We do not have to care about this at all here because we're just looking at the voltage at that point. So that would equal 0. And then this is just -2 over 200 minus J500 equals V out over 2400. If we multiply both sides by oh no, if we just multiply both sides by 2400, yeah, you get V out equals 20 what is this? Yeah, it's going to be -4800 over 200 minus J500. We can remove 2 zeros from the top and the bottom. We get -48 over 2 minus J5. And then if we multiply this by, let's see. Yeah, multiply this by 2 plus J5 over 2 plus J5. We're going to get 48 times 2 is -96 minus 48 times 5 is 240. So -96 minus J240 over 2 squared plus 5 squared is 29. That's a scary number. But anyway, then you just do the division and you'll get -3.31 minus J 8.28 for V out. So now that we have that, we want to find S of the load. We'll call it SL. And as I said earlier, you can use this equation, so you can always use this equation, right? And then you'd find I is equal to V out over ZL. And then you take that and you would use it in this equation, right? Or to make our lives easier, if you remember the equation, you can use S equals 1/2 V squared over Z conjugate. So alternatively, getting a phone call. The hell? Okay, let me check this. Okay, that feels like spam. Whatever. Okay. Anyway, so going back to this, yeah, alternatively, S equals 1/2. This is the one we used on a previous page somewhere. I feel like we did. Maybe we didn't. Whatever. It's V squared over Z conjugate. So S equals 1/2 V squared over Z conjugate. So then 1/2 V squared, right? That's actually going to be, or the magnitude of V squared equals V out times V out conjugate, which is going to be -3.31 minus J 8.28 times -3.31 plus J 8.28. And if we do that, it's going to be 3.31 squared plus 8.28 squared, which gets us to 79.25. Of course, you could do all this in your calculator if you wanted to. I'm just writing out all the steps. And then the ZL conjugate, right? Remember, the conjugate is just this with the sign flipped. So it's 1000 minus J1000 instead of plus J1000. So then we have 1/2 times 79.25 over 1000 minus J1000. And make sure you don't square this again, because remember, this formula is for it already being squared. So you don't have to square it again. So then when you do this, you you're here, you say, yeah, the easiest way to do this is you can do this in either way, you've already done it, but this is actually pretty clearly going to be it, it's kind of clear. It's root 2 times 1000 e to the j negative 45. This is just because if you're like at 1, 1 or 1, negative 1, then you have like a 1, 1, and then this is going to be the square root of 2. So if you have 1000 and 1000, then this is the square root of 2 times 1000. And then if you just have a square, the angle is 45 degrees. So, and then that is like 14.2-ish. So since you can do that pretty easily, then you could say, okay, it's 1/2 times 79.25 e to the j 0 over 14.2 e to the negative j 45. And that will give us a final answer of about 0.028 e to the j 45 degrees. And that would be the complex power dissipated, or the complex power associated with our load resistor. So again, like I said at the beginning, as long as you know your power equations, then it's like not really anything all too new. Um, it's just find your complex power, find your complex voltage, and then either use, you know, this equation or this equation and find the thing they're asking you to find. So, yeah, I think we're about out of time. Does anyone else have any other questions? Anything else you want me to cover real quick?
Could you go back to the first page you wrote the equations on?
It's
Oh,
a
here,
page 4.
sorry.
Yeah, it's okay.
The maximum power transfer, ZL equals ZL star, or is it?
Um, let me
That's L, right?
I might yeah, wait, I might have that wrong. Let me find this in
Should be ZTH.
yeah. This part doesn't matter. Because what you find is for the when you're looking at the P average, you only care about the RL. But for yeah, just ignore that. You do have a Z star in this equation though. That's important. That comes from because if you're like solving, if you're going from here to here, then the I star kind of moves the Z star. The star you still have the conjugate. If you don't have the conjugate, then you won't end up getting the right thing. But yeah, this was just me being wrong. I mixed up the equation. But this is the
Okay.
maximum power transfer equation. It's with the you only care about the resistive component of your load. Because when they're
Mm.
asking about if there is a question on the quiz about maximum power transfer, it will likely only ask for the power average because that's the equation that you learned about. Mhm.
Okay, thank you.
No problem. Anything else? Okay. In that case, I'll end the recording.